Hello everyone, my name is Brant Kudrowski at the University of Wisconsin-Oshkosh. In today's organic chemistry video, I'm going to talk to you about mass spectrometry. I'm going to cover concepts like inside a mass spectrometer, what happens and how does it work? We'll talk about introducing ionization and fragmentation, try to explain those concepts. I'll explain how molecular ions form, and we'll talk about locating a molecular ion in a mass spectrum. I'll also talk about M+1 peaks, explain where they come from, and also M+2 peaks and what you can learn from them. I'll talk about the nitrogen rule and then determining the number of carbon atoms in a molecule once you locate its molecular ion. Finally, I'll also talk about how molecular ions vary in intensity and how you can use that to try to identify them in a spectrum and be sure you're not missing any. Stay tuned. In the next video, I'll talk more about other mass spec concepts, including fragmentation in a lot of detail. Hope you enjoy the video. Today, we're going to be talking about mass spectrometry, and we're going to discuss what that is and what it can be useful for, how you can use it to help you identify molecules or bits of molecules. Mass spectrometry is oftentimes abbreviated MS for mass spectrometry. It's a technique that involves an instrument called a mass spectrometer, and I've got here a diagram of a typical mass spectrometer to try to help you understand how the apparatus works. So I'm going to move around here and talk about where things start. So first of all, on the left side, there's a chamber that contains a neutral molecule, your sample. So essentially you have a molecule, you want to analyze it, you stick it in this chamber. The chamber is at a really high temperature and the molecules enter the gas phase. They vaporize when they enter this chamber. And there are neutral molecules here then in the gas phase, and there's a small tube that runs into this tube-like structure here. It's kind of a bent tube that goes over this way. This tube is under vacuum, so it's had all of its air removed by a vacuum pump, and the molecules then move into this evacuated tube, and they move in past some plates. This is called a repeller plate, and it is kept at a positive potential, so it's positively charged, and then there's some negatively charged accelerating and focusing plates. Then there's a filament. This is a wire that is emitting high energy electrons. So the electrons come off of this filament and they move through the ionization chamber, and as the molecules enter this chamber, they get hit by this stream of electrons and that ionizes them. It bounces an electron out, makes them positively charged. And once they're positively charged, they can be moved around with these plates and electromagnetic fields. So a positive molecule, a cation, would get repelled by the repeller plate and want to move down the tube that direction towards the negatively charged accelerating plates. And these ions then, these cations, move through and they fly through the slits in these plates and they end up going down the tube at high velocity. And they move straight until they encounter this curve in the tube. And at that point, there's a magnet. And what the magnet does is able to adjust the trajectory of these ions. Magnets exert a force on ions, and it depends on how heavy the ion is and how fast it's moving and how strong the magnet is. So some of the time they'll be basically bent, the trajectories of these ions will be bent a little bit, but maybe not quite enough, and they'll not quite negotiate the turn and they'll crash into one side of the tube. They might be overcorrected, they might be bent too much, in which case they'll crash into the other side of the tube. But if they have just the right amount of correction, if the magnet bends their trajectory just enough, they'll get through the tube, they'll pass through a slit at the end, and they'll hit a collector that essentially generates an electrical signal when ions hit it. And then the computer can collect that data and plot on a spectrum all the ions that it sees when it sees them. And the thing about the apparatus is that it can be adjusted. So you can adjust either the acceleration velocity based on the charges you put on these plates, or sometimes the magnet strength can be changed. But essentially you can select for whatever mass ion you want to get through, and you'll know what mass it is based on the values you put on the charge plates and the value of the magnet. So essentially what this is a mass sorting tool, and you can sort through all the masses and then you can count the masses, and what you get here is a graph of the abundance of all the different ions that you see. So every peak on this spectrum is in the up direction. It's telling you there's a certain number of atoms of a particular mass, and this is what a mass spectrum is. In this next segment, I'm going to talk about an introduction to ionization and fragmentation in mass spectrometry. So this is what happens inside of the ionization chamber of a mass spectrometer. And to start things off, I'm going to use a simple example. I'll use methane. That's a C with 4 hydrogens bonded to it, CH4. This molecule has a mass of 16 AMUs, or atomic mass units. I get that from considering carbon to be 12, because 12 is the most common isotope of carbon. Also considering hydrogen to be mass of 1, because 1 is by far the most common isotope of hydrogen. So you add 12 and 4 hydrogens and you get 16. Now that molecule is neutral, so this is one that's not going to show up in a mass spectrometer. It's invisible in mass spectrometry. The instrument cannot move it around because it has no charge. But when it enters an ionization chamber, that changes. When it's hit by a beam of electrons and an electron gets bounced out, it becomes a radical cation. And one way to think about that is to imagine one of the electrons in one of the carbon-hydrogen bonds being bounced out to give a structure that looks like this. Where here I've shown the original molecule, but missing one electron, and that electron I'll draw down here as an E-. In reality, the dot and the positive charge aren't localized in one spot. So a better way to draw this molecule would be to, instead of showing the cation and the dot being in one spot, draw CH4 and then put brackets around it and put a cation and a dot, indicating a radical cation. This thing still weighs 16, so it would give a peak at 16 m to z mass to charge ratio on a mass spectrum, because it weighs 16 atomic mass units and it has a positive charge now, so the mass spectrometer will move it around, push it through the tube, and the collector will collect it and the computer will detect it. This molecule can then fragment, where it loses pieces to make it smaller. And the thing that can break off of this molecule would be the loss of an H dot. So if a hydrogen atom were to break off and float away, we would get a molecule that's got one fewer hydrogen on it, and therefore would give a peak that's 1 mass unit lighter. Peak at 15 m to z. And there'd be an H dot, which is a neutral atom. So that's one that doesn't show up in the mass spectrometer. The mass spectrometer only detects positive species. This can fragment again, giving CH2 cation and another hydrogen atom, H radical. This would give a peak at 14 m to z. The process can just keep going, giving another piece that's smaller with a peak at 13 mass to charge ratio, and finally a peak at 12 mass to charge ratio when the final H dot is lost. So we're going to see this fragmentation process play out with bigger molecules, and the fragmentations are going to be more complicated than H dots floating away, carbon pieces breaking off and floating away. But this is an introduction to explain how it works and to explain why mass spectra have so many peaks. There's a molecular ion piece that forms, which is the molecule itself just missing an electron, and then there's usually a whole series of fragments, which are cations, but they're smaller than the original molecule because something has broken off and floated away. And by looking at both the molecular ion and the fragments, it's possible to get a lot of good information about a molecule, about how big it is and what kinds of substructures it might contain. All right, so now I'm going to talk about what happens in the mass spectrometer when ionization happens. I'm going to sketch this out with a generic example. I'm going to say here's a neutral molecule, And I'll represent that as just a capital M to indicate that this is a neutral molecule, doesn't have any charge. And then ionization happens when it enters the ionization chamber, when it gets hit by a high energy electron in the electron beam in the mass spectrometer ionization chamber. Ionization, that produces a radical cation and one electron. And this is the molecular ion right here. It represents the entire molecule. All the atoms that were in the neutral molecule are still in the molecular ion. The mass of these is the same. It's just this one has a positive charge, and it appears as a peak in the mass spectrum. Then there'll be fragmentation reactions that happen. And there will be cations and neutral radicals that will get formed. There'll be both types of things. These will appear as peaks. These will not appear as peaks, but we'll notice that they're being produced because we'll see masses being lost. And we're going to talk about this fragmentation process in a little bit. But first, before we get to that, I want to talk about the ionization process so you can understand that a little bit better. This is going to be about understanding ionization and molecular ion formation. When a molecule is impacted by an electron in a mass spectrometer, it loses an electron, but where it loses it from depends a lot on the kinds of electrons that the molecule has. So here's how a molecule loses electrons, the order that it happens in. Non-bonding electrons are lost first. If you have a molecule that has electrons that are non-bonding, like lone pairs of electrons, those electrons are the easiest ones to lose because they're the least tightly held. They're not forming bonds, so when you lose one of those electrons, it doesn't result in a big destabilization of the molecule. When you break a bond, you destabilize a molecule, but when you lose one from like a lone pair, the energetic penalty isn't as great. So they're easy targets. So here's an example of a molecule that has non-bonding electrons. This is the molecule acetone. Acetone has an oxygen, a carbon, a CH3 here, and a CH3 here. But importantly for this discussion, it has two lone pairs of electrons. And so when this goes into an ionization chamber in a mass spectrometer, it loses one electron, but it loses one of these out of the oxygen lone pairs. That's what happens first. So what you would expect to get for a molecular ion from acetone would be this. You would have one of the lone pairs still intact, and then one of the dots in one of the lone pairs is gone. It got bumped out by the electron beam, and so this is the radical cation. This is the molecular ion of acetone. That's where the electron got lost from. That's one example. Let's take a look at another example with a nitrogen species. Here's one where the molecule has a lone pair on a nitrogen. And in ionization, in a mass spectrometer, again, the easiest electrons to lose are the ones that are in the lone pair. So one of these two electrons, and it doesn't matter which one you pick to show going away, just erase one of the dots and put a plus charge in its place, and you'll have the molecular ion for this molecule. That species would look like this. It's a radical cation on nitrogen, and there's an electron that was lost. That's ionization in a molecule that has lone pairs. And understanding this is important because this will help you understand later on when a molecule fragments, why it fragments. A lot of it has to do with where the charge is, and we're going to see that becoming important in a little bit. The next type of electron that's most easily lost are electrons in pi bonds. Electrons in pi bonds are lost next. So if you have a molecule that has no lone pairs, but it has a pi bond, the pi bond electrons are going to be the ones that are going to go away in this molecule when it loses an electron. So here's an example of that. This molecule contains a carbon-carbon double bond. And this is a neutral molecule. It has no charge on it yet. The double bond here is 4 shared electrons. So if you remember the structure of a double bond contains 2 different kinds of bonds. There's a sigma bond and then there's a pi bond here. The pi bond is the weaker of the 2. Electrons in pi bonds are held through overlapping p orbitals, which are not as good at sharing electrons. So pi bonds are inherently weaker than sigma bonds. When this molecule loses an electron, it isn't any one of the strong sigma bonds that loses an electron, it's the weaker pi bond. So when this molecule ionizes, it's one of the electrons in the pi bond. Here's what my molecular ion is going to look like. All the atoms are still present, and we're just stealing 1 electron out of the pi bond, and I'll put a dot there and a plus charge here. There used to be 2 electrons that were shared between these 2 atoms. In place of this, there were 4 electrons total, 2 here and 2 here, but we took one of them away, and now that's a positive charge. So here's our radical cation, the molecular ion for the molecule that contains a pi bond. Electrons in single bonds, in sigma bonds, are lost last. That's because these are the strongest of the different kinds of bonds. Sigma bonds are stronger than pi bonds, and the hierarchy of stability is sigma bond electrons are most tightly held. They're the hardest to lose in ionization. Pi bonds are weaker. Their electrons are more easily lost, and the lone pairs are the least tightly held electrons. Those are lost most easily. Here's an example of a molecule that contains just sigma bonds. So this molecule is going to be an alkane, and this is just a representative example. But it's a molecule that just has sigma bonds. And so when this molecule ionizes, it's going to lose an electron from one of the bonds. And I've got carbon-carbon bonds here, and I have carbon-hydrogen bonds too. In fact, what I think I'm going to do is draw out the hydrogens on one of the methyl groups. Just so we've got it here and we can look at it. When this molecule loses an electron, it could either come out of one of the carbon-carbon bonds or one of the carbon-hydrogen bonds. And you don't really know which one that is. So a lot of times what people will do when they're trying to represent a molecular ion of this type is they'll just draw the molecule like I'll do here, and then they'll draw brackets around it, and they'll say plus dot for radical cation. And that's meaning this is a molecule that's lost 1 electron. We're just not specifying where it is. And it's just a representation that is going to be like a more detailed way of drawing M plus dot. Okay, now that you have an idea of what a molecular ion is and how it forms, we need to talk about where do you find it in a mass spectrum, and then how can you use it to help you identify a molecule. So here's a spectrum of a typical molecule. This is a spectrum of hexane, the structure CH2, CH3, CH2, 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 CH3, a simple alkane. This is its mass spectrum, and the boxes are pointing out peaks of interest. And I just want to tell you, first of all, finding the molecular ion, what you want to do is look to the right side of the spectrum at the heaviest substantial peak. The heaviest peaks are the ones that have the biggest numbers down here. So the number on the x-axis is m to z, that's mass to charge ratio. That's what determines how the ions get filtered out by the mass spectrometer. And what I'll tell you is that for this course, the vast majority, all of the examples we're going to look at, they have just one charge, a +1 charge. The Z down here is going to be 1, and the mass then can be exactly read right off the x-axis. In other words, if you look at this spectrum and you can see there's a peak here at 29, that means that's a molecule, a cation that weighs 29. Remember, all of these peaks are from cations. Only cations show up in the mass spectrum. Neutral molecules do not show up. We can infer their presence when we see a molecule breaking into smaller and smaller pieces. Something is breaking off and floating away. That's a neutral thing. So we've got on the x-axis mass to charge, which is just a direct measure of mass when Z is equal to 1, as it's going to be in this course. And then on the y-axis, there's relative abundance. This tells you how much of that ion is produced. If you look at the heights of the peaks, it tells you how important is that ion. So if we look around here, we can see, for example, at 75, there's nothing. There's no ion that gets produced that weighs that much. But if we look around here, we see a really intense peak at 57. That's the tallest peak. What we're going to learn to call that is the base peak. The base peak is the most abundant ion in the spectrum. It's labeled as the base peak, and then the y-axis is set based on that. So the tallest peak defines the tallest unit here. So think of that as 100%. Everything else is scaled relative to that. If you look at the 29 peak here, it's about 42, 43% or so. That's 43% as intense as the base peak. So it's all scaled relative to the base peak. And the base peak is important to think about because it's the most abundant cation. It's also the most stable cation. These cations are produced not randomly, but they're produced in order of stability. The ones that give really big peaks are really stable cations, and it'd be good to figure those out. And we're going to spend some time deciding how to do that and talking about that. So the molecular ion is the heaviest substantial peak. So on the x-axis, you want to go all the way to the right and look for the biggest substantial peak. And the reason I say that is almost all molecules have a small, what's called M+1 peak here. And that's what's called out here at 87. So at 87, you can see there's a little peak here, and then there's a bigger peak at 86. It turns out 86 is the molecular ion, and the peak at 87 is what we call an M+1 peak. That's a little bit of a trick to try to figure out what's the molecular ion, what's the M+1 peak, and just not to get confused by them. So now what we're going to do is talk about where does this M+1 peak come from, and why is it not a big deal? What does it mean? And so we're going to talk about that next. When you have a molecule, like say for example, CH4, that is methane. If you consider what the molecule weighs when carbon is carbon-12, and then each one of the 4 hydrogens is hydrogen that weighs 1. The isotope of hydrogen here is just hydrogen with a proton and no neutron. That's by far the most common isotope of hydrogen. Carbon-12 is the most common isotope of carbon. That's carbon that has 6 protons and 6 neutrons. But that's not the only isotope of carbon. Carbon-12 is about 99% carbon-12, but there's also a little bit of carbon that's carbon-13. About 1% of all naturally occurring carbon is carbon-13. It's just 1 mass unit heavier. It still behaves chemically like a carbon. It's got 6 protons. It just happens to have an extra neutron. It's got 7 neutrons. So think of it as like heavy carbon. And when you have a molecule like CH4, there's a 1% chance that that carbon might be a C13. And when you add up the masses of the atoms in all these scenarios, the molecule where it's carbon-12, well, that one weighs 16 atomic mass units. And then if you look at the one that's got a C13 in it, well, that one weighs 17 atomic mass units, because it's just got that extra neutron. And the abundance of this would be 99%, and the abundance of this one would be 1%. And so when you look at a mass spectrum and you look at the molecular ion region, you would see a large peak at 16 and a much smaller peak at 17 mass units. That's your molecular ion, that's your M+1 peak. It turns out that hydrogen is like almost exclusively H1, so you don't need to worry about isotope with hydrogen. It's always going to be 1, hydrogen 1. Carbon is 12 most of the time, 99% of the time, but 1% of the time it's C13. So when you look at molecular ions of carbon-containing molecules, they're going to have an M+ peak and then an M+1. So this peak at 16, that'd be the M+ dot. And then this one would be what we call M+1. It's still a molecular ion. It's just a molecular ion where there's a C13 in it. There is a lot of information embedded in a molecular ion, and so it's important to locate it, to know what its mass is, and then try to learn as much about it as you can. We talked about molecular ion and M+1 peak. Sometimes there are other isotopes that can generate significant M+2 peaks. So one of the things you want to look for is look to see, is there a substantial peak that's 2 mass units bigger than the molecular ion. So what I'm going to say here is a large M+2 peak. That's a peak that's 2 mass units higher than the molecular ion. If you see one of those, not an M+1 peak, that's only 1 mass unit higher, but if it's 2 mass units higher, that suggests chlorine or bromine. Either chlorine or bromine. One of those 2 atoms is likely present in the molecule if you have that pattern. And what you'll see specifically is the signature for chlorine is an M+2 peak that is about 1/3 the abundance of your molecular ion. So that's the signature for chlorine. The signature for bromine is an M+2 peak that is about equal to the abundance of M+ dot. So let's take a look at an example to illustrate what you would see and why you would see it. So here's an example with chloromethane. This is a molecule that contains a carbon, 3 hydrogens, and a chlorine. The thing about chlorine is naturally occurring chlorine exists as 2 isotopes. You could look at all of the chlorine that's out there. There's a chlorine that weighs 35, and there's a chlorine that weighs 37, based on this one having 2 extra neutrons compared to this one. And the abundance of this is basically there's 3 parts this to 1 part this. 25% of chlorine is like this, and 75% of chlorine is the chlorine 35. So the lighter one is more abundant. If you have this molecule, Cl, CH3, you're going to have chlorines of both types. There's going to be 2 types of chlorines. You're going to have a peak that weighs for when the chlorine is chlorine 35. So if you've got a chlorine 35 and a carbon and the 3 CH3s, well, that molecule, that's 50 AMUs, atomic mass units. So you'll see a peak at 50. And then the thing is there's also a version of this that has the heavier version of the chlorine. So there's a chlorine 37 variant out there that you're also gonna see in the mass spectrum. And that has a mass of 52 AMUs. That's 37 plus 12 plus 3. You get to 52. So there's going to be a 52 peak, and it's going to be 1/3 the height of the peak at 50. When you see this, M+ dot and M+2 and they're in this 3-to-1 ratio, that is telling you chlorine. And then remember, in addition to that, this molecule, there will be a small amount that contains a C13, so you're going to see a little peak there. And then at 53, you'll also see you might see a very tiny peak. That would be this molecule where instead of a C12, there's a C13. Basically, though, it's the two big peaks that you want to worry about. That is telling you chlorine. All right, let's take an example, or look at an example that contains bromine. So we'll do the bromine version of that molecule that we looked at just previously, BrCH3. The thing about bromine, so naturally occurring bromine, exists as two isotopes. There is a bromine 79. And when you add up all of the protons and the neutrons, you get 79. And then there's one version of bromine that weighs 2 mass units more, and that's an 81. And they are present roughly in a 1-to-1 ratio. It's not a perfect 1-to-1 ratio, but for our purposes, it's close enough. And interestingly, there is no such thing as a bromine 80. And this gets a lot of people confused because they'll look at the periodic table and the mass that it lists below the big Br symbol is 79.9, looks like 80. The thing is, though, is that mass in the periodic table is the average of all the isotopes. So if you take bromine 79 and an equal amount of bromine 81 and you average the masses, you get 80. But you will never find a single bromine that weighs 80. Bromine is always either 79 or 81. And when you have a molecule that incorporates that, like this, there are two possibilities for what kind of molecular ion you might get. You might get the one with the lighter bromine or the one with the heavier bromine. Your mass spectrum is going to look like this. There's going to be a version of the molecule that has a bromine 79, and then there's going to be a version of the molecule that contains the heavier bromine 81. These things are going to be separated by 2 mass units. And they're going to have peaks that are roughly the same intensity. So the bromine 79 example weighs 94 mass units. This one has a mass of 94. When you take 79 and 12 and then 3 for the hydrogens, you get 94 atomic mass units. And the one that contains the heavier bromine 81 just weighs 2 more, so that's 96. And then since they contain carbon, they're also going to contain little M+1 peaks that are going to be just 1 mass unit higher than each of those two. That's what a bromine looks like. Equal intensity molecular ion peaks separated by 2 mass units. All right, now I'm going to tell you about something else you can do with the molecular ion that will help you understand some things about a molecule. It's called the nitrogen rule. And what the nitrogen rule says is that if a molecule has an odd number of nitrogens, it will have an odd molecular ion mass. So molecules with an odd number of nitrogen atoms, and that would be like 1, 3, 5, have odd massed molecular ions. Just put a bullet point next to that. And then molecules with an even number of nitrogens atoms, and that would be 0, 2, 4, and so on. 0, we'll call 0 an even number. These have even masses. Even massed molecular ions. All right, let's give this nitrogen rule a try with a couple of examples. Here's an example that contains 1 nitrogen, and let's figure out what its molecular formula is. It's got 1, 2, 3 carbons, C3. For hydrogens, it's got 3, 6. There are 2 here, 7, 8, 9. and then it has a nitrogen, and the carbons all weigh, we'll consider them to weigh 12. So when you're adding masses in mass spec, just consider everything in its most abundant isotopic form. Carbon is 12, hydrogen is 1. If you've got a chlorine or bromine, that's a little different, but we won't worry about those examples just right now. But the carbons are going to give us 36. 3 times 12 is 36. We're going to get 9 from the hydrogens, and then the nitrogen is going to give us 14. So we've got 36 plus 9 plus 14. So 36 plus 9 is 45, plus 14 is equal to 59 AMU. So that is odd. Let's go over here and check out this example. This molecule contains no nitrogens. That would be an even number, so we predict the mass would be even based on this nitrogen rule. Okay, so for this example, we've got a molecule that has just carbons and no nitrogens. So we've got 4 carbons, and then we've got 3, 6, 8, 10 hydrogens. So 4 times 12 is 48, plus 10, 1 for each hydrogen, gives us 58 atomic mass units. And you can do this with any example you want. If you're looking at a good Lewis structure of a neutral molecule and it's got 1 nitrogen in it, it's going to be odd. If it has no nitrogens in it, it's going to be even. And those are going to be pretty much most of the examples we're going to look at. We're not going to look at many examples where we've got 2 nitrogens or 3 nitrogens. They're certainly important and interesting, but it's just kind of beyond the scope of this class to worry about those kinds of examples. So when you look at a molecular ion, just note, is it odd or even? If it's odd, think probably got a nitrogen in it. If it's even, probably no nitrogen. So that's a useful thing to know. Here's one more little bit of information about the nitrogen rule that is good to mention. The nitrogen rule applies to molecules that contain the following atoms: carbon, hydrogen, oxygen, sulfur, nitrogen, and X, where X is a halogen: fluorine, chlorine, bromine, iodine. They don't have to contain all of these, but if it contains just these atoms or some subset of these atoms, the nitrogen rule works. So there are potential examples where if you've got an exotic atom in a molecule, it might not work, but we're not going to see any of those. And these atoms cover the vast majority of the organic molecules that you'll see. So the nitrogen rule basically works pretty much all the time. One of the other things you can do with a molecular ion once you've identified it is you can get a sense of how big the molecule is. And you can even put an upper limit on the number of carbons that it might contain. So here's an example. Suppose you had a molecule, a mass spectrum, where you identified a molecular ion and it had a mass of 86 atomic mass units. Okay, so that's a molecule of a particular size. To figure out what are the maximum number of carbons, just divide it by 12, because every carbon weighs 12. So max carbons, take 86 divided by 12, and what you see is that gives you 7.2. Well, you can't have a fractional carbon. Carbons come in 1, 2, 3, 4, 5, 6, 7, 8, but they don't come in 7.2. So what you do is round down, and that means 7 carbons max is as many of this as this molecule can have. Now that doesn't mean the molecule has exactly 7 or close to that, but at least it tells you it doesn't have 8. And so if you wanted to, if you knew this molecule had only carbons and hydrogens in it, you could start figuring out what are some reasonable molecular formulas that would get you to 86 if you consider that 7 is the maximum number of carbons it could have. So here are some hypothetical formulas that you could start to work with. So you could say, well, maybe I've got C7. C7, max number of carbons, if you take 7 times 12, that's 84. And then if you figure that 86 is the mass, so there'd only be 2 hydrogens in the molecule then. that, you can draw the formula up there, but that's not really going to be possible to get a good Lewis structure out of that molecule. There's simply no way to connect 7 carbons and only have 2 hydrogens. It just isn't going to work. So what you can do is think about, well, maybe there aren't 7 carbons, but maybe there are 6. So this one isn't really going to work out, but maybe there are 6 carbons, and 6 times 12 is going to be equal to 72. And then the balance of this has got to be hydrogens. And if we're trying to get to 86, there must be 14 mass units due to hydrogen. So H14, when you add those together, you get 86. So you get 72 mass units from the carbons and 14 from hydrogens. That's a molecule you can draw a good Lewis structure around. That'd be isomers of hexane. So 6 carbons and 14 hydrogens you can make a lot of good Lewis structures out of that. Things get more complicated when you have molecules that have oxygen or nitrogen in them, because those don't weigh 12. They have a similar mass to carbon. You don't want to get too bogged down in trying to figure out what's a formula that's going to fit a particular molecular ion, but at least you can get an idea of how big it must be and how big it cannot exceed. So a certain number of carbons is the most it can have. That can be somewhat useful sometimes. One last thing I want to talk about with molecular ions is that they vary widely in intensity. Sometimes molecular ions are strong and easy to see, and other times they're very small, difficult to see. Sometimes they're not visible at all. It's just the way it goes in real molecules. Here's an example of a molecule where there's a very strong visible molecular ion peak. At 64 AMUs, you can see a molecular ion very, very strongly. In fact, this is also the base peak, so that can happen. The molecular ion and the base peak can be the same. The base peak is simply the strongest signal in the spectrum, and it happens to be the molecular ion in this case. Then there is an M+1 peak at 165. This happens to be the structure of eugenol. This is a molecule that's found in cloves that's responsible for making cloves smell and taste like cloves. Here's another example of a mass spectrum that's interesting. This is one where the molecular ion region is a lot more subtle. Way over on the right-hand side, you can see a molecular ion, in this case at 206, but it's not very big. Then there's a corresponding M+1 peak at 207, but again, you have to be kind of careful and know what to look for. It doesn't jump out at you. This is just because the molecular ion in this molecule happens to be a little bit less stable than it was in the previous example, probably a lot less stable, and it tends to fragment to give a really strong base peak. In this case, that's a lower mass fragment. This happens to be the molecule eugenol acetate. This is another molecule that's present in cloves that contributes to cloves' aroma and taste. It's kind of a minor flavoring component in clove oil. Here's a final example that's really challenging. This molecule has a molecular ion at 130 AMU. That is so small and so insignificant you wouldn't even know it was there. Most people would want to go take a look over at the other side of the spectrum, over here at 80, 85, 86, 87, probably would think that 87 was the molecular ion and that 88 was the M+1 peak. The problem is that's not the way it is, and this happens sometimes with molecules. Some molecules just have such fragile molecular ions that they do not give a noticeable peak. Now, this isn't something that I expect you to figure out or know, and I won't give you an example like this on an exam, for example. But it does come up in real molecules, and if you're looking at a mass spectrum that has one of these molecular ions is essentially invisible, I'll tell you where it is so that you don't get confused. But just realize that molecular ions vary in stability a lot. Some of them are strong because they're stable cations, some of them are weaker because they're less stable cations, and some of them, like in this case, are so unstable that they don't show up as a peak at all. They just disintegrate before they get to the detector. This happens to be the molecule isopentyl acetate. This is a molecule that's present in bananas and contributes to making bananas smell and taste like a banana. That's an introduction to molecular ions. In subsequent videos, I'm going to talk about how molecules fragment. Once you get a molecular ion, what happens to it? How does it fragment? What kind of pieces come out of it? And what can you learn from that? If you found this video useful, check out the next one in the series or watch the prior video. And consider subscribing to my YouTube channel. My name is Brant Kudrowski. Thanks for watching.